Analytical Chemistry 1, Lesson 12. Let's look again at confidence intervals or limits. In essence, it is a way to expand the sample standard deviation to account for the number of replicate tests performed and to adjust for the level of probability you would like to assign to your answer. If you knew the population standard deviation of your experiment, the probability density distribution could be described by a Gaussian function, and some multiple of that standard deviation could be used to define integration limits, which would define a confidence interval. In practice, however, it's more common that our experiments consist of a small number of replicate measurements. From that we can determine the average, the sample mean, and the sample standard deviation, just the square root of the sample variance. The distribution, however, is no longer a perfect Gaussian. While its shape is similar, it is broadened. The exact nature of the distribution depends upon how many replicates you performed. As the number of replicates increases, the distribution narrows until as n approaches infinity, the Gaussian distribution is recovered. The mathematical description of this new distribution involves gamma functions or beta functions. The key results, however, have been tabulated many years ago by a statistician named Gossett. Gossett was employed by the Guinness Brewing Company in Ireland. He was concerned with trying to understand how sampling their ingredients and product could be used to ensure the product quality. He could only take a few samples of hops, for instance, but wanted to know how confident he could be about the entire shipment. What did taking 3 samples, for instance, tell him about the whole population? His employer worried that if he published his work, then their competitors would learn that they were studying these statistics and might start to copy them. So he was permitted to publish this, but under a pseudonym. He chose to publish in a journal called Biometrica and did so with the pseudonym of Student. His work continues to be known under the name of Student. Just for interest's sake, here is the front page of his seminal journal article. Take a look at the last paragraph on this page. He reminds the readers that the main analytical objective is typically to try to determine the probability that the population mean, the true mean, is within a certain distance of the sample average. It was assumed that the measurements would be distributed normally, a Gaussian distribution, and that we know the population standard deviation. This would happen when we are very familiar with the technique over a long period of time. Each time you take a measurement, you do not know how close you are to the true mean. But when you take several measurements and average them, you start to narrow down your uncertainty. This is when we return to the concept of confidence intervals. Recall from before that the interval involved some constant times the standard error of the mean. And recall that the standard error of the mean is the standard deviation divided by the square root of the number of measurements. We know both of these variables, so how do we decide on the constant by which to multiply the standard error? The decision is based, in the first place, on our choice of confidence level. If we are working with population standard deviations, then we know the errors are distributed normally. The constant multiplier comes from the Gaussian distribution, plus or minus 1 standard error, or sigma over root n, and you can be confident to about 68%. Plus or minus 2 sigma over root n, and you're about 95.5% confident. So, a requirement for a higher probability requires scaling sigma over root n by an increasingly larger number, which comes from the integral of the Gaussian distribution function. This multiplier has been called z, and the confidence interval under these conditions is given as x bar plus or minus z sigma over root n. The edges of the window are z standard errors above and below the average. When sigma, the population standard deviation, is used, z is fixed for a given confidence level. It gets larger as we approach 100% confidence, and as we perform more measurements, the confidence interval shrinks as root n, while x bar drifts towards the true mean. But there was a problem for Gossett. He did not have the population standard deviation. He was concerned with the problem of having only a few samples. Instead of sigma, he only had s, the sample standard deviation, and the distribution was broader than the Gaussian. It was his t-distribution. In this paper, he showed how integrating over these new t-distributions for the desired probability led to his improved confidence limits with the expression of x bar plus or minus ts over root n. The value for t was, like z, dependent upon the desired confidence level. However, unlike z, it also depended upon the degrees of freedom. As n approached infinity, t approached z. But for any finite number of measurements, t was greater than z for a given confidence level. Finding t or z for a given confidence level usually involves using the student's t-table. The degrees of freedom in this measurement is n minus 1. It is minus 1 because 1 degree of freedom has been used in specifying the sample average. So making 2 measurements means you only have 1 further degree of freedom. If you made 31 replicate measurements, you would have 30 additional degrees of freedom. Each column identifies the scaling t-value that identifies the upper and lower integration boundaries for a t-distribution, for the specified probability, and for the numbers of degrees of freedom. Notice how the t-values get smaller as n increases. This reflects the greater certainty that one can have when more data has been acquired. The confidence interval is narrower for the same probability. Note also that as the desired probability increases, the numbers get larger. This indicates that the confidence interval must widen if we want to be more confident that it includes the true mean. It is very common for people to use the 95% column. Now, you've probably heard during campaign seasons when pollsters report their results and specify that their results are considered accurate 19 times out of 20. And there's your 95% confidence. Look how the infinite degrees of freedom row has the value 1.960. Very commonly, you will find scientists reporting their results by just multiplying their standard deviation by 2 and claim 95% confidence. Can you see how it is more complex than that? I want to make sure you appreciate what is happening when you choose different values for z or t. Here's a Gaussian function, which we use when we are assuming that the errors are distributed normally, which would be true for a well-defined experimental system, or with very many samples measured. We're looking for a value for z once we have chosen a probability for a confidence interval. We have the standard error of the mean, which is just the standard deviation divided by the square root of the number of samples n. If we choose plus or minus 1 standard error, then we have a confidence level of about 68.3%. If we integrate this curve between these two limits, we get 0.683. Symmetrically, on either side of this region, there are 2 other regions whose areas are each 15.85%, which are the regions excluded by this confidence interval. Those values would arise by integrating from minus infinity to minus 1, or from plus 1 to plus infinity. If instead we chose plus or minus 1.645 times the standard error, then we have a confidence level that includes 90% of the area under the curve, with 5% excluded on either side. If we're looking for 95% confidence, then we have to choose z equal to plus or minus 1.960. This leaves 2.5% on either side. Because 1.96 is so close to 2, this is why you will often hear people say that they are giving the results for plus or minus 2 standard errors. Finally, this is what you'd be looking at when seeking 98% confidence. In this case, z is plus or minus 2.326, and we have, of course, 1% left out on either side of the curve. This was using z because we assumed that the distribution was normal, because we knew the value for sigma, the population standard deviation, because this experiment was well known. And where do we find those numbers, 2.3262 and 1.960, etc.? This is when we refer to the table of students' t-values. At the bottom is the row for infinite degrees of freedom. This is where the t-distribution becomes the normal distribution. Most commonly, a table of t-values also includes the z-values at the bottom. Look for infinity under the degrees of freedom. There's another thing to check for. These tables can be prepared in 2 different ways, and you need to check in the description or the title to find whether the table has been prepared for 2-tailed or 1-tailed tests. Commonly it is 2-tailed, but you need to make sure before pulling any numbers from it. When we are making up confidence intervals, we need 2-tailed values. The excluded regions appear both above and below the confidence interval. For example, in the 95% confidence region, the 2.5% above it and the 2.5% below it were not included in integration, 2 tails. Here is our normal distribution again. When we integrate from minus 1.645 to plus 1.645, we obtain the result 0.90, or 90%. The integration from minus infinity to minus 1.645 gives 0.05, or 5%, and the integration from plus 1.645 to plus infinity also gives 0.05, and we have a 2-tailed distribution. But if we have a 1-tailed problem, we may instead seek the integration from minus infinity all the way to plus 1.645, which gives 95% in the target region and 5% above it. The integration limits are the same. 1.645 is used from the two-sided 90% limits and also for the one-sided 95% limits. The tables are often just listed for either one-sided or two-sided, and you can find the numbers for one type in another column of the other type. It is worth mentioning at this point that while tables such as these just have a few different columns for different probability levels, the process could be done for any probability. There could be a column for 91% or 92% or even 93.498%. Such a table would be unwieldy and cumbersome. A collection of 4 or 5 probability levels is usually sufficient for most purposes. However, the values are now available as functions in Excel. For instance, the function norm.s.inv 0.95 equals 1.64485, what we've been looking at. It produces the z value for the one-tailed normal distribution at the 95% level. This tells us that 5% of the curve is found above 1.64485. But by symmetry, you can also conclude that plus or minus 1.64485 are the limits for the 90% two-tailed distribution. Here's another example. What if we wanted to identify the confidence at the 87.5% level? Well, the Excel function gives us 1.15035 for the one-tailed distribution. Notice that this is closer to the mean, and so the excluded region constitutes 12.5% of the area under the curve. But if we wanted a two-tailed distribution, then we would have 12.5% excluded on the other side. And 12.5 plus 12.5 equals 25, or the two-tailed distribution would be for the 75% probability. A little quiz for you. What if we wanted 87.5% two-tailed distribution? Well, we would need to split the 12.5% into 2 and seek the integration limit for 6.25% probability. Since this function takes the integrated area from minus infinity up to the desired integration limit, we enter as the argument for norm.s.inv 1 minus 0.0625 equals 0.9375. The function returns 1.53412, a number nicely between 1.645 and 1.150. So it makes sense. So all of this discussion has to this point been based on the assumption that you have the population standard deviation sigma and are dealing with errors distributed according to a normal or Gaussian distribution. But that is not normally the case. We, like Gosset, usually have a finite number of samples to deal with and only have a sample, not the population standard deviation. How are things different? Well, first of all, the errors are distributed according to Gosset's, or other students' t-distribution. The curve is similar to that of a Gaussian, but the mathematics are very different. The function now depends not only on the mean standard deviation, but also on an additional variable, the number of degrees of freedom. While the curve rather looks Gaussian, it is instead shallower at the center, and the wings stretch out more. By the way, do not worry about the mathematical form of these functions. You will not need to recall them for the course. Just know that they exist and you could look them up if you needed to. With this new distribution, we can do exactly as done with the z variable, except that now we not only must choose a probability level for our confidence interval, but must also specify the number of samples. Here again is the t-table. The values for the z variable are in the bottom row. Above that, for each probability or confidence level, are numbers for the t variable at several finite numbers of degrees of freedom, which recall is the number of samples minus 1. Note how the numbers are larger as we go up the column. And as we have fewer samples, the t-distribution gets wider and wider in order to continue to contain, for example, 95% in the integrated area. The integration limits get further and further away from the central value of the average. The result is that to maintain 95% confidence, the limits on our confidence interval must increase. Consider that we have the same standard deviation and with 5 samples. The degrees of freedom is 5 minus 1 equals 4. From the table for 95% confidence, we find 2.776. Recall that if we felt we were dealing with population standard deviation, we could use the value at the bottom of this column, namely 1.960. With the normal distribution, we would be able to set the confidence limits up to plus or minus 1.960 times the standard error. But with the t-distribution, we set the confidence limits to plus or minus 2.776 times the standard error. Having a small number of samples requires that we expand the confidence limits in order to maintain the same level, 95%, for instance, of confidence. As with the normal distribution, Excel has some built-in functions for the t-distribution as well. t.inv.2t 0.05 and 4 is 2.77645, which is just the number that we've got here. This is the two-tailed t-distribution for 4 degrees of freedom. Now this function wants us to put in the excluded probability, 0.1 minus 0.95 equals 0.05. Sorry, that's just the way they wrote the function. They do have a one-sided function as well. It's just t.inv, 0.025 and 4. It gives minus 2.77645. Note that you had to enter 0.025 instead of 0.05 to get the same integration limit as for the two-tailed case, except because it is left-tailed, you get the negative value. Here we have some experiment with a population mean of 10,000 and a standard deviation of 1,000. Each trial consisted of 4 measurements, and a sample average and sample standard deviation were determined for each trial. In the upper panel, confidence limits are 50%, of 50% are calculated, while 90% limits are found in the bottom panel. The only difference is the value of t. Open square data points are those in which their confidence limits include the true mean. Filled black squares are those which do not include the true mean. Note how 50% of the trials do not include the true mean in the top panel, while only 10% of the trials do not include the true mean in the bottom panel. The 90% confidence intervals are much wider than the 50% intervals, but now we are more confident that a trial we complete includes the true population mean.